Good morning, students. In the previous lecture, we discussed briefly about optical sensors, and we mentioned how transmitted energy from the transmitter sensor and received energy or power from the receiver determines the range of communication between the two and how the received information is affected by distance. Okay, the first step to study this is mathematical modeling of the transmitted energy as a function of distance, the received energy as a function of distance. One way of modeling is the inverse square law. The inverse square law says the received power or received energy is inversely proportional to the square of the distance between the transmitter and the receiver. So, for example, if we observe a flashlight, observing a flashlight, nearby objects look brighter than faraway objects. Light beam becomes wider and dimmer as its distance from the flashlight increases. It is similar to electromagnetic radiation. The energy decays exponentially with distance. It decays with distance from the transmitter. So there is a threshold received radiation level where data transmitted is no more reliable. So the variation of the received power with distance can be modeled by the inverse square law. The threshold radiation level is a level that determines the maximum range of communication, the maximum range between the transmitter and the receiver. And as I said, a mathematical modeling of an electromagnetic intensity with range is usually inverse square law. The inverse square law applies to light radiation. So if we see here, for example, I have a beam of light transmitted here. When we go far from the transmitter, what will happen from the flashlight or from the torch? The intensity decreases. The intensity here, if I have here a wall, if I assume this is wall, so the light is the light spot here. This the area of the light spot here at this point is smaller than the area of the light spot at this point. So the area is bigger here. That means the intensity is smaller at this distance compared to at this distance. So as we go far away from the flashlight, the intensity decreases. What is the intensity? The intensity refers to the total power divided by the beam spot area. So the unit is in watts per meter square. As the distance between the flashlight and the wall increases, the beam spot becomes larger and dimmer, and the intensity of the wall and the intensity received at the wall decreases. So that means if I have a certain light detecting receiver at far location, because the intensity is smaller, then the received power by the detector will be smaller. See, this is the example here, a transmitter. At this distance, I have this area, beam area, and this distance, beam area. So the beam area increases with distance, meaning the intensity decreases. But the received power for that specific receiver will decrease because the intensity is decreasing. Intensity is equal to the transmitted power divided by the beam spot area. So the intensity at a reference distance R0 or R0 equals transmitted power divided by the area at distance R0. If the range is increased by a factor alpha, where R equals to alpha times R0, so the intensity will decrease by alpha square. Why? Because the area is proportional to distance square, so r square. So this will be alpha square minus r naught square. So if I have to calculate the intensity at a distance r equals to alpha times r naught, this is equal to the power p over the area at alpha times r naught. So the area at alpha times r naught is alpha square over the area at the reference distance r naught. So that means this is equal to 1 over alpha square, the power transmitted divided by the area at a distance r naught. If we say this P over the area at a distance r naught equals to the intensity at a distance r naught, then the intensity at alpha times r naught is equal to the intensity at the reference distance divided by alpha square. See, inversely proportional to distance. So let's take an example. Consider a 6-watt light bulb that provides 6 watt of light power. If the beam forms a spot with an area of 2 meters square on the wall that's 4 meters away, and the reference distance is 4 meters. So the intensity at the reference distance 4 meters is 6 watt over 2 meters square, 3 watt per meter square. Then what will be the intensity at 20 meters, for example? So to calculate this, we need to find alpha. Okay, the value of alpha in terms of we have to compare it with the reference distance r naught. Here, alpha times r naught is equal to 20 meters. That means alpha is 5 meters. So the intensity of the light at 20 meters is the intensity at 4 meters divided by alpha square, which is equal to 0.12 watt per meter square. So the intensity decreases with distance. So this is how the receiver is receiving. The receiver captures the intensity. So if I capture the intensity, for example, within 1 meter square, if the area of the receiver is 1 meter square, so at a distance 20 meter, I will have the intensity divided the area, so 1 meter square, it will be 0.12 watt. However, at a distance of 4 meter, if I capture it, if I multiply this by 1 meter square, I have 3 watt. So the intensity at 20 meter is very small, very, very small compared to the intensity at 4 meter. So the receiver detects the electromagnetic radiation. The electromagnetic radiation, and it produces an output power. And the produced output power at a distance r equals to alpha times r naught is the power at the reference distance r naught divided by alpha square. Okay, so we can apply the previous light intensity to power. So to power concept, when we assume power, that means transmitted power from the transmitting sensor and received power from the receiving sensor. So the receiver always detects the receiver, of course, it detects in the presence of a random noise. So for that case, we need to have a threshold power level, P tau. The threshold power level determines the maximum range of communication. That means if the received power is below the threshold power, then the receiver cannot detect, no detection. So that means the sensor will not be working. To detect a signal, the power produced by the receiver located at a distance r must be greater than the threshold power, P tau. So the maximum range of communication is can be calculated from the threshold power. So P, the power received at the maximum distance, is P tau, the threshold power. That means the maximum distance is alpha max times R naught. Now, as I said earlier, there is a threshold power that is important for communication between the transmitter and the receiver, and it determines the range. Here, for example, a power delay profile where it shows the power is exponentially decaying with distance. That means the received power. So at this point, if I see at this point, this is the received power. So when the signal is present, it's well above the threshold. So it can be detected correctly, that means. And at a distance R2, 2 times R1, if you see here, it is also above the threshold power, then it can be detected. And at this distance, this is the maximum distance. At maximum distance, I have the threshold power p tau. And at this distance, for example, if you see at this distance, the threshold is here. So it is the received power is below the threshold, the required minimum power. So that means it cannot be detected. It cannot be detected by the receiver. Okay, inverse square law applied to a beam interrupt sensor. Okay, let's have a beam interrupt sensor that counts packing crates or packages on a conveyor belt where 2 meters separates between the transmitter and the receiver. Okay, I will go back to this, what it means, I will explain. So that means here I have a transmitter, here I have a receiver, and there is a package coming in between here. So it will the sensor will count the number of packages passing between the transmitter and the receiver beam. So when the beam is interrupted, that means there is the package, so the counter will count. And if the beam is not interrupted, then there is no package that and it will not be counted, that means. Okay, so let's have a beam interrupt sensor that counts packing crates on a conveyor belt where 2 meters separates the transmitter and the receiver. At this 2-meter range, which is the reference distance, the detector output power is measured to be 100 times the threshold power, 100 times p tau. When a crate is not blocking the beam, at a distance 2 meters, that means the received power is 100 times P threshold. What is the maximum range at which the beam interrupt sensor will still count? So remember that the beam interrupt sensor will count until the minimum required power, until a distance where I have the minimum required power, which is P tau. So at that point, I have maximum range. So the received power at that distance, which is alpha max times R naught, is the received power at the reference distance divided by alpha max square. So this is equal to PD at 2 meter over P tau, the threshold power. So PD at 2 meter is 100 P tau, and divided by p tau, I have alpha max is equal to square root of 100, which is 10. That means the maximum distance is alpha max times 2 meters, that is 10 times 20 meters. So this beam interrupt sensor can count until a distance of 20 meters between the transmitter and the receiver at a range of at a maximum distance of 20 meters. Okay, let's talk about digital cellular telephony, the concept of threshold power to digital cellular telephone. In the simple case, the simplest case, the received power from a transmitted antenna, for example, a transmitted mobile phone, can be modeled as inverse square law. The received power at a certain distance is follows inverse square law. Inverse square law means the received power is inversely proportional to the distance square. Okay, let's say the transmitting antenna in a cellular system transmits sufficient power to a receiver located 10 meters away, and it produces 10 to the power of 5 times p tau, the threshold power. So that means 100,000 times the threshold power. What is the maximum range at which the receiver still detects the signal? Remember, the 100,000 times p tau is the power at the reference distance R0. So at the reference distance R0, I have 100,000 times p tau. So at the maximum range, I will have p tau. So P, the received power at the maximum range, which is alpha max times R0, is the received power at the reference distance times alpha square max, which is p tau. So, but we have P at the reference distance is 10 to the power of 5 times p tau over alpha max square. So alpha max square is 10 to the power of 5, which is alpha max is 316.2. Therefore, the maximum distance is 316.2 times R0, the reference distance, which is equal to 3,162 meter or 3.162 kilometer. Only when the distance between the transmitter and the receiver is less than or equal to this distance, the maximum distance, for the intensity of the transmitter radio signal to be sufficient for the receiver so that the receiver can detect the transmitter signal. Now, there are a number of, in a digital cellular system, there are a number of base stations. What are base stations? Okay, I go back here, I go here. This is, for example, a certain area. This area is served by different base stations. Base stations means these transmitting power stations, and they transmit power to everywhere. So the mobile detects the transmitter power from the base station. So here, for example, the transmitter tower from it can be from ECENT here. So each base station serves a certain cell, and we call this cellular communication, because this is a cell. You see here the shape of it looks like a cell. So it can be, the base station can be at the center or it can be somewhere depending on the design. So each base station serves a certain cell. So when the receiver mobile phone becomes far away from the base station, that means the received signal will be smaller and smaller. So the distance between the base station and the receiver mobile phone determines the amount of received power, or it determines the quality of communication between the two. So let's go to this example. I have here a base station antenna here, another base station antenna here. In between, I have a cellular telephone here. So the concept of received power can be used to determine the location of this cellular telephone. So it can be used for localization. That means, so the concept of received power can be used for localization. That's how, for example, in our mobile phone, the authorities, they can know where we are located if we have a cellular mobile phone by using this concept. So this is a two-dimensional example in a 2D concept. So I will show you how we can determine what is R1 and what is R2 from the received power. So let's say this mobile antenna receives a power from the two base station antenna 1 and base station antenna 2. And let's determine the location of this mobile antenna based on the amount of the received power. Determine the location of the cellular telephone from the power of the detected telephone signal. Assume the power produced by antenna 1 from the detected telephone signal is twice that produced by antenna 2. So the received power at this telephone from antenna 1 is 2 times the received power from antenna 2. Okay, so determine R1 and R2 where the distance between the two antennas is 10 kilometers. Okay, now the two antennas are identical. We assume a simple case the two antennas are identical. So the received power at a distance R0 is the same and it is obtained by performing calibration. The received power P1 at, that means the received power from antenna 1 is at a distance of alpha 1 times R0 is the received power at a reference distance R0 divided by alpha 1 square, and the received power from antenna 2 at a distance alpha 2 times R0 is PD R0 divided by alpha 2 square. Now the received power from antenna 1 is 2 times the received power from antenna 2. That means PD R0 over alpha 1 square is equal to 2 times PD R0 over alpha 2 square. Now, since we assume the two antennas are identical, the received power at the reference distance is the same, so this will cancel this one. And from this relation, we get alpha 2 is equal to square root of 2 times alpha 1. But we know that R1 plus R2 is equal to 10 kilometers. So that means what is R1? Alpha 1 times R0. What is R2? Alpha 2 times R0. Alpha 1 times R0 plus the square root of 2, because alpha 2 is square root of 2 times alpha 1. Square root of 2 alpha 1 times R0, which is equal to 1 plus radical 2 times R1, because why R1? R1 is alpha naught times alpha naught times R0. This is R1. This is R1. So alpha 1 times R0 is R1. So 1 plus square root of 2 times R1 is equal to 10 kilometers. From this, R1 is 4.412 kilometers and R2 is 5.858 kilometers. So as we see from this calculation, we determine the distance R1. That means the distance of the mobile phone from transmitter 1, from transmitter base station 1, and the distance R2, the distance of the mobile phone from transmitter 2, in a way that means we determine the exact location of the mobile phone between the two base stations, between antenna 2 and antenna 1. That's why I said earlier that the concept of received power from mobile phones is used for localization. Localization means the location of the receiver or the location of the mobile phone. And this is how in telecommunication, in mobile communication, they used this concept for localization. Of course, R1 is R2, since the power received from antenna 1 is greater than the power received from antenna 2. Okay, so in this chapter, we try to give a brief introduction about sensors, especially digital sensors, binary sensors, and optical sensors which use electromagnetic energy or like infrared light, and simple sensors like mechanical switches. And we discuss how threshold power is important. That's the minimum power that is used the minimum power that can be used to detect to detect a received information, or that means the sensor can be located at maximum distance, Rmax, provides that it satisfies the threshold power requirement. And we discussed about optical proximity sensors used in barcodes, and we discussed about inverse square law, which determines the maximum operating distance or range. And we discussed about how inverse square law can be applied in cellular telephone systems and how it can be used for localization. And thank you for listening to this lecture.